Thank you for the intro. Thank you everybody for the really warm welcome. So let me get started. What I want to tell you a little bit about today is the fact that small models are taking over now. And the reason why that is the case is now we have industry-leading companies like Apple, for instance, telling us about their architecture and how they're doing it. And that gives a lot of validation to the approach. We have been working in this space for a while now, and so I would love to contrast and compare what Apple is doing with what you can do with open source tools that we've been developing, Ludwig and Lorax, and also what you can do in a platform like Predibase. All right, so I don't know how many of you have watched the WWDC where Apple was introducing the Apple Intelligence capabilities? Show of hands? A few, okay, sounds good. For those of you who have not seen that, they showed a bunch of technologies, and the most impressive from my point of view is what actually they are able to do on device, because they also use a mix of on device and out of device machine learning and LLMs, but what they do on device is particularly interesting. What they're able to do is they're able to do basically GenAI capabilities on device that are personalized for the user and specialized on specific tasks. And so there's a bunch of them, like for instance, they use it for doing proofreading, they use it for doing summarization, they use it to do it to derive bullet lists from messages, to adjust the tone of writing. So there's all these sort of capabilities that are going to be available in the, I think, 18.1 version of iOS, right? But how do they do this? They also discussed about that. And how can you also you do it with using open source tools and using platforms? The traditional way of basically doing generative AI, and when I say traditional, I say since the beginning of 2023, so it's like a year and a half of history here, we're calling it traditional, basically is I want to use whatever is the larger best model that can solve my problem, and that's all I need to do, really, right? The problem with this is that these models are too big, too expensive. They're also really slow, depending on the specifics of each model, but and also too general to work specifically on each use cases. The consequence of that is that the cost of ownership of these models gets to a point that is not sustainable for most organizations. And the other big disadvantage is it's not private, it's not in your control, right? And what Apple did is, this is quoting from their blog post, is they basically started to utilize adapters. Adapters are little pieces of models that are attached to the main model, and I will go a little bit more in detail about them in a minute. And these adapters are fine-tuned for specific tasks. By doing that, they managed to make the different tasks that I was showing you before work really, really well on device. Because the base model that they would have on device would not be good enough for solving these tasks, but with the fine-tuning of the adapters, they actually managed to do that. So this is the first ingredient. And there's going to be a second ingredient, hold to your seats for the second ingredient. But let's focus on this first ingredient to begin with. And so instead of using a large model, what you can do if you want to mimic the Apple's approach is you can start to use smaller models that are open source, and basically by fine-tuning them, you can bring them to the level of quality that is required for your applications. The advantage is that on one hand you can get better performance than large models for this at a substantially lower cost, with lower latency, and also you own the model and the data. So it's all in your control. When we started investigating this approach somewhere in the middle of last year, this is the first thing that we tried, basically. We wanted to see if we could fine-tune a smaller model. In that case, it was Llama 2. So again, middle of last year. It seems super far away, but there was a moment where Llama 2 was the best model, right? The best open source model. And we compared Llama 2, which is on this task of like Colonel Plus was name identity recognition, with GPT-4. And as you can see, Llama 2 gets it right 33% of the time, GPT-4 66% of the time. So if you were not to do anything else, you would conclude that, I should use GPT-4 for this. What we did is we fine-tuned on the task both Llama 2 7 billion and Llama 2 70 billion. The difference between 70 and 7 after fine-tuning is very, very small between them, but it's very large with respect to a non-fine-tuned model like GPT-4. In this case, was more or less 40% more accurate and was 250 times smaller. So 3 orders of magnitude smaller, which also means, cheaper to run, less expensive, faster to run. But because this was very successful, we said, well, let's try it on many different tasks and see if this pattern holds across many tasks. And here you can see on the x-axis, there's all the tasks that we tested it on, like 31 different tasks. And on the y-axis, you have the delta, so the difference between the performance of GPT-4 and the performance of the fine-tuned models that we fine-tuned on these specific tasks. So on the left, the tasks on the left basically just show that you can match easily the performance of GPT-4. The one in the middle show you that in some cases, you could get better performance than GPT-4, and the ones on the right are the ones where the performance is substantially better than GPT-4, while, again, being very small models, very cheap and very fast to run. And so we published this, and we called it LoRa Land, and so it's online, you can go and check it out. It's pretty fun because you can choose the data set, and you can choose some examples from the data sets and see what like a base model would do and what a fine-tuned model does, and the difference in the quality that you get. And you can play around with those. It's very fun. But the technology behind it is what we actually baked into our platform. And then we released also the fine-tuning index, which is a living document that you can find online on our web pages that contains a comparison of the performance of many different base models. So not only Llama 2, but all basically the open source or the main open source models with respect to the closed source ones. And here you can see the dark blue parts of the bar is the performance out of the box without fine-tuning. And you can see that actually GPT-4 is, among these models, actually the best. This is like averaged across 31 different tasks. It's actually the best on its own among all of them. But when you add the light blue part, the fine-tuning, most open source models actually outperform it, and even the very small one reach a performance that is very, very close to the one of GPT-4. So very recently, and now I don't remember exactly anymore, like a couple of weeks ago actually, Llama 3.1 came out, and so we updated all our experiments to incorporate that. And at the same time, there's new models that OpenAI came up with, so GPT-4o and GPT-4o Mini. And so we really wanted to compare with those models to be able to understand what, if, even after these updates, there was still an advantage for open source models. And actually, the pace of progress of open source model is outpacing, like the slide that I've showed before, the pace of improvement of non-open source models. And so as a consequence, Llama 3.1 from 8 billion fine-tuned in our experiments shows that substantially better performance of both GPT-4o and GPT-4o for Mini. And similarly, that is true also for Zephyr. This is like another example on open domain question answering. You can get substantially better performance, in particular if the data that you're doing fine-tuning on is very unique and different from like general internet data, and this is like shown in this case. And finally, I would say OpenAI also introduced capabilities of fine-tuning GPT-4o Mini, and for us, using Solar, which is like a model provided by Upstage, which is like we have like a company we collaborate with in providing the base models. If you fine-tune a Solar model on a specific task, in this case for enhancing text, you get better performance than even GPT-4o Mini fine-tuned. So open source across the board is the way to go, and fine-tuning open source models across the board is the way to go. Hopefully after this, like next time that we do this event, I will see more hands showing up for how many of you have fine-tuned. Hopefully this was convincing enough. But how does it work in practice? So I will get a little bit into the nitty-gritty details. Hopefully that's useful. When you train a model, actually what you do is you run the model forward, meaning you provide some inputs and get some output. And then you evaluate a loss and update the weights depending on the outputs. And so the right part here is that W is the weights of the model that get updated during a backward pass. If you do that for fine-tuning your models, that's not great. It actually works well in terms of the quality of the output that you get, but it's very, very slow because you're updating all the weights of the models, and it's also very memory intensive because the gradients of those weights are like at least 3 times bigger than the weights of the model themselves, and it's also very, very expensive. So what we do, and in general, adapters like the ones that Apple is using do, is actually add these little pieces, A and B, on the side of the model. And when you do the fine-tuning, you just change those A and B weights. And these weights are, different parameters may lead to different number of weights, but usually it's between 0.1 and like few percentages of the weights of the original model. The consequence of that is that you can train them much faster, much easier, and without using as much memory, so on cheaper hardware. And it works as well as if you were updating all of them. This is like a table coming from the LoRa paper, and you can see these are all different tasks, and the comparison is basically shows that there's basically no difference in performance between doing entire fine-tuning or doing performance efficient fine-tuning. The difference, though, comes in the number of parameters that you're actually modifying, and so it's a fraction of the parameters that you would modify, and that makes it for a cheap and very fast process. If you want to do this, Ludwig is our open source project that makes it very, very easy through the declarative configuration to do fine-tuning of your own models. It's in the open source, you can check it out and try it out. We also have in Predibase an enhanced version that I'm going to tell you about in a minute. The second piece, the second ingredient that makes the Apple approach work is the fact that, okay, now I have all these adapters, but if I'm naive about it, every adapter would need to be served with their base model. And so if I'm naive about it, the cost of serving all these adapters is linear in the number of adapters that I have, right? What they do is something very smart, which, again, we also do with LoRax. We dynamically load the adapters that are needed for a specific task, and they are hot swapped from memory. And this gives basically the ability to the base model to adapt dynamically to what is the request coming from the user for the specific task while running, basically. We do the same thing with LoRax, really. If a naive way of deploying one of these adapters would be to, again, use a base model, attach the adapter to it, and serve it on its own GPU, for instance, right? What we do is we make it possible so that all these different colored, in this case, adapters can be hot swapped. And so you need the resources of, basically the same resources of serving one model can serve hundreds, literally hundreds. And the mechanism, it's basically has some weights in memory that are swapped. Here you see, like on the left-hand side, there's an example with just one type of an adapter, and so those blue weights are the weights that are added on top of the yellow weights, which are the weights of the base model. And in the case of LoRax on the right-hand side, you have in memory both the blue and the red weights, and when there's a query for the green, then the greens are hot swapped on the fly at almost no cost. And you can see that from this like throughput graph, where on the x-axis here you have the number of fine-tuned models that you're serving, and on the y-axis you have the throughput, so higher is better. And if you're naive about it, there's the dark yellow ochre line that shows how the performance would degrade with adding more and more adapters. But if you use LoRax, we did so many optimizations, including some specific kernels, CUDA kernels that we use, that it makes so that the yellow line is basically flat. You can add more and more adapters and you don't degrade the throughput. And the same is true for latency, by the way. The effect of that is that basically if you have the cost of ownership of multiple models basically stays flat if you use a solution like Predibase that uses LoRax, while if you have to do it with something like OpenAI, it grows with the number of fine-tunes that you do. LoRax also is open source. You can check it out, and both LoRax and Ludwig, we use them internally at Predibase, and so they are really well supported by our community. And but basically, Predibase, what does, it's like brings these two technologies together and glues them into like a coherent platform that is already ready to use and deploy for enterprises. And the platform, what it allows you to do is to both prompt, fine tune, and then serve open source models. And it's very easy. You first connect your data, then you can customize your models by fine tuning them using Ludwig. We basically have a concept of repositories so that you can do multiple fine-tunes and compare the performance of all these models. And then when you're happy, you can deploy them. And they are deployed on a scalable infrastructure that uses Kubernetes and runs on the cloud. There's multiple interfaces. One, it's like code interface through a Python SDK, but there's also a UI that makes it easy for, in particular, for monitoring and for managing multiple runs and multiple experiments of a team. And the environment where you can deploy that is basically either we deploy it for you as a SaaS deployment, or you can deploy it on your virtual private cloud. The advantage of doing that is that we have for some further optimizations. They make it so that we get even faster inference. And for instance, here we show like a graph where we use Turbo LoRa, like an innovation that we just put out like less than a month ago. That fine-tunes not only for improving the quality of the models, but also for making them faster. And Arnav, like in his next talk, will dive deeper into that. And that's a unique feature in Predibase that nobody else has, and it's like very powerful. At the same time, on the side of fine-tuning, the fine-tuning you can do in Predibase is way more effective than what you could do with just the open source, both in terms of quality, we can get better quality out of the box, and also in terms of speed. Our experiments show that it's actually 6 times faster than if you were to do it using open source technologies, right? So bringing these two things together makes for a platform that is like cheaper, faster at inference, faster at training, and easier to run. All right, so if you want to check it out, we also have like a booth in the back, and there's a demo, and we can give you a demo and try it out. Hopefully, I convinced you that fine-tuning open source models is the way to go. And yeah, happy to take a few questions if you guys have them. Thank you so much. There's a question here. Also, please, Michael, Dav, keep me honest with time. I don't know how many questions.
I think time for 2, maybe 3 questions.
Great.
Really quickly, hot swap. When you mention that, so say there's 2 adapters running on the same Llama 8.
Yeah.
What's the latency if you like had 10 requests to the same adapter and then intersperse 10 more requests to a different adapter? Is it a little bit more latent, or is it exactly the same latency as if it was 10 in a row?
Let me show you. Here it's throughput. You can imagine it's basically the same graph flipped for latency. You can see that the difference between 0, 1, and 4, there's a little bit of a difference there, but then it's flat, right? And the reason is because we have a multi-tiered system of cache. There's GPU cache, CPU cache, and then on disk, and usually the disks that we use are NVMe disks, so they're also very, very fast. The worst case scenario is still fast, like adds less than 10% latency in the P99. So because of that, and again, the worst case scenario means like an adapter that is never used, right? So for that adapter, it's actually worth to pay the cost, because the alternative would have been for you to serve that adapter and never being used ever, and be like 10 milliseconds faster. That's specific one instance that it happens over the course of a month or something like that, right? So on balance, it's substantially better. There is like a little cost that you can see there that you have to pay, but it's like a minimum compared to the both overall both latency and throughput, and in general the cost would be like 1,000 times larger, right? One more question. There's one there.
So for fine tuning, right, you need 3 things: model, data.
So because we're doing live stream, do you mind waiting
Yeah.
for a second for the? Yeah, thank you so much.
So for fine tuning, right, you need three components: the model, the data set, and the platform. So we covered the model, the platform. What is the most reliable and the scalable way to build the data sets that work for your use case?
Yeah, that's a great
Thank you.
question. Also because, for several reasons. So in our experiments, like, those 31 data sets, they range from like 1,000 data points to 500,000 data points. And what we've seen is that it's not a direct correlation between how many data points you train it on and the final performance that you get. Obviously, if you have more data, that's better. But it's not that if you don't have, like, you get bad performance when you have 1,000 data points, for instance, right? And our rule of thumb, I would say, when we talk with customers, is that 1,000 data points is a really good starting point, right? But in some cases, for some applications, people don't even have those 1,000 data points, and that's a barrier of entry. To try to, diminish that barrier of entry and making it lower, we actually did a webinar earlier this week to show how you can use techniques like synthetic data generation that Gretel is gonna talk about to bridge the gap, basically. And you can have 10 data points and generate some like 1,000 to 10,000 data points of synthetic data, and the performance you would get is very, very close to what you get if you had 10,000 real data points. So the way to bridge that gap is by synthetic data generation, in my mind. Sure. All right, I think I'm out of time. Thank you very much again, and happy to chat with you later.